explainable and control zero-shot image generation and in data-limited domains architectural framework present.
Yep. Hello, I'm here.
Hello, so the floor is yours.
Thank you. Just a second. I'll share my screen. Let me just find it. Let me know if you can see it.
Yes, it looks perfect here. I know anyone cannot see, anyone unable to see. Okay, so let's carry on.
Thank you. Good afternoon. My name is Serhiy Tchaikovsky, and today I will be presenting our research on a new architectural framework designed to make text-to-image generation more explainable, controllable, and accessible, specifically for domains with limited data. This work was conducted at the Kharkiv National University of Radioelectronic and addressed the intersection of the generative AI and formal software engineering. Well, modern models, generative models like DALL-E and Midjourney are showing impressive results. They face critical limitations for professional use in data-limited domains. They work as opaque black boxes, and they require massive GPU clusters, and they are hard to control precisely. Furthermore, they suffer from the cold start problem. If you are a specialized designer, artist, or researcher with a small, unique dataset, like specific medical imagery or a niche artist style, these general models often fails to adapt because they require massive amount of training data that simply does not exist in your field. So our goal isn't just to build another model, but to propose a software architecture. We aim to integrate three distinct technologies that are domain adaptation, multimodal control, and explainability into a cohesive system that follows strict software engineering principles. Currently, most solutions in this area are just a collection of ad hoc scripts. So we wanted to move away from that and create a formal design with loosely coupled components that ensure the system is reliable, maintainable, and extendable. The proposed software architecture will be built upon three pillars. We would use GANs for their speed and disentangled latent spaces. Then we would use clip to understand text. And finally, we would use XI to provide transparency. We specifically chose GANs over diffusion models for this framework because GANs allow for much faster real-time manipulations of specific image features, which is essential for the interactive control we are trying to achieve. Currently, researchers use these technologies as separate tools, but our framework unifies them into a single pipeline. I would like to introduce you the core concept of our contribution. We propose 6 design principles that are separation of concern, formal interface contracts, loose coupling, technology agnosticism, non-functional requirements, and composability. The most important aspect here are technology agnosticism and formal interfaces. This means that we define how components talk to each other, but not what they are. If a better text encoder replaces clip next year, or a better generator replaces style gun, you can easily swap them out without rewriting the system, provided they adhere to the interface contracts. Here, I would like to present the high-level architecture view, which consists of 3 layers. The user interacts via a lightweight web client, which is layer A, while the heavy lifting happens on the server side in the core framework, which is layer B. Notably, we have a dedicated explainability layer, layer C, It monitors the generation and explains it back to the user. The flow is circular and interactive. The user provides intent, layer B generates the image, and layer C immediately analyzes it. Layer C then sends visual feedback like heat maps or silency maps back to the user, explaining why the image looks the way it does, allowing for informed refinement. Moving from the logical design to physical deployment, this figure illustrates our solution to the hardware barriers. By adopting a strict client-server model, we offload the computationally intensive tasks such as GAN generation and clip guidance to remote GPU server. The user only needs a standard web browser to interact with the system. This addresses the non-functional requirements of computational accessibility. It opens the door for academical labs, startups, and small businesses to use state-of-art generative tools without need to invest $1,000 in local GPU clusters. This architecture delivers three specific properties. It provides user with the fine-grained control, such as adjusting a slider for a specific feature. Also, it provides transparency, showing how exactly the AI interprets the prompt. And it also data efficient, capable of learning new styles from a few examples. This data efficiency is achieved through few-shot domain adaptation. Because the architecture is modular, we can fine-tune just the specific weights needed for new style without retraining the whole model, making it feasible to create custom generators for very niche domain. And to visualize this, let's imagine the situation for an industrial designer. He has the task with creating a new design for a chair, for example. The system explains why it looks that way it's generated. For example, the designer may want to change only the back's height. In standard models like Midjourney, for example, a new prompt might alter the entire chair, changing the legs, colors, resulting in an entirely new design. In contrast, in our framework, the designer adjusts a specific parameter, slider, for example, defined by the architecture, and the system updates only the bucket's height while preserving the rest of the image. In conclusion, we have presented a blueprint for the next generation of AI tools. Ones that are not just powerful, but also understandable and controllable. Regarding the promising direction for future researchers, we have identified three key phases. The first one is the practical implementation and prototyping of the system based on the specifications we established. The second one is empirical validation. We will test the system against the specific metrics defined in our paper, such as time to target and user trust score, to prove its efficiency. And the first one is the pattern formalization. We aim to document these architectural patterns to help standardize the development of future generative systems. We believe that applying these software engineering principles, modularity, formal interfaces, and separation of concerns is the necessary next step to move generative AI from novelty to a dependable professional tool. Thank you for your attention, and I'm happy to answer your questions.
So thank you. Are there any questions from the floor, from the audience? It was a very interesting presentation. Just a couple of questions I have to satisfy my own curiosity. You said that you move the computational burden over to the server side. So if we were to estimate server strength, let's say, so how strong should it be? What kind of server? Is it a very expensive one that only maybe Amazon can afford, or is it one that a university could afford?
Well, the idea here is that university can afford. It's possible to start this server application, for example, on the Amazon servers, and to rent a couple of GPUs, and it shouldn't be, take too much in cost. So it should be below, for my formal computation, about 5,000 per month, I suppose. I will need to check it more.
Euro, you mean?
Well, dollars. There
Dollars,
were.
whatever. But
Yeah.
in terms of more like processor capacity, I was curious.
Well, the idea was to use GPUs similar to NVIDIA for fourth generation 460.
Okay.
Amazon doesn't have exact. Yeah, sorry.
Just one of them or more?
Well, start from one and then to check whether it would be sufficient for this configuration. If not, then it's possible to expand it. That's why the cloud computation here is benefits, because it's easier to increase GPU power here.
Okay, and with such a configuration, how many simultaneous users could it satisfy?
Well, it's something that I will need to check in my further research.
Just a rough, it's not really necessary to commit now. Maybe couple or about 10 or 100 or something of order of magnitude, let's say.
I was thinking about starting about from 1 to 10 GPUs and check whether it will be sufficient for some part of the for some amount of users, and then it's possible to to scale it.
Okay, and the second question is again of scaling. You said that you can add new styles without affecting the model. So when do you have to start scaling again up, I don't know, memory or capacity of the model? How many styles can it accommodate? So what is the relation between number of styles and maybe the parameters of the model, like memory or whatever else is defining strength?
Yeah, well, the idea here was to use models like StyleGAN, so and to have like a zero-shot approach here. So we will, in this case, we will like eliminate the need to train models for new styles. And how to preserve them, this is something I would try to think for the further researches, because the idea was start from two ways. One of them is some sort like a designer, and the second one is artists for small studios who want to release some sort of games, and I will think how to split it here.
Okay. All right. Thank you again. Any other questions from the audience? No? So let's move on to the second presentation. It's by Nural Huliev and Oleksiy. Research on hyperparameter tuning methods for implementing the random forest algorithm based on medical and psychological data. Someone present here for this paper? No? Paper number 80. Okay, so let's move to paper number 92 by Rodion Bukhanevich and Andrei Selestov, Semantic Segmentation and the Limited Availability of Labeled Data. Someone here to... hello?
Yeah.
Yes.
Hello.
It's a little bit...
Let's,
yeah, now it's better. Okay, so the floor is yours.
Okay, wait. Wait. A second. Wait. So you see the presentation, yes? Please give me some
It is
feedback.
quite visible, yes.
Quite visible, okay. Good day, everyone. The research I'm presenting today is on topic semantic segmentation under limited availability of label data. Me and my scientific head, Professor Andrei Shelistov, we elaborated new methodic. So the research I'm presenting today addresses a fundamental challenge that sits at the interaction of artificial intelligence and Earth observations. The main topic: how do we perform accurate semantic segmentation of satellite imagery when we have very limited labeled data available? There is a significant bottleneck that like consistency emerge across all applications that already has people faced like different Earth observations, medical diagnostic, agricultural monitoring, and others. The central challenge is how do we construct a robust feature space mathematical representation that can reliably capture semantic similarity between different objects. In the domain of satellite imagery, semantic segmentations, acquiring label data is exceptionally problematic for like main reasons that we need annotators that understands how in our task land cover classification, vegetation types, and geographic patterns. And also it's time consuming. So how do we challenge this? How do we solve these challenges? First of all, let's talk about related work. So it can be split into 4 parts. Deploying for Earth observations in the left upper corner. So it's all deep learning about satellite imagery. Then some based fundamentals about contrastive learning, and next 2 parts, feature selection for vegetation mapping. So in our research, we will compare our results, first of all, with third article in the feature selection for vegetation mapping part. This genetics algorithm that selects features for training classification or segmentation tasks, and some semi-supervised conceptions about new conceptions about improvement of segmentations. So let's talk about data we used. So in our research, we used Sentinel-2 satellite imagery dataset that consists of projects we worked with provide us dataset of images and masks. So each image is 64 and 64 pixels, and for each image there is a mask that splits into 3 classes: background, healthy vegetations, and stressed. Also, each image consists of 13 spectral bands, and all data set conducted in around 400,000 pixels that can be classified as stressed forest symptoms. Also, we should explain about vegetation indices. Vegetation indices, why we should explain is because we compare our results with article I have described before, is genetic algorithm that produced good features for classification. And this algorithm works with vegetation indices. There are 3 indices we have worked with. So, for example, we vegetation indices is like quantitative descriptors that tell us about vegetation condition based on spectral properties. So these indices aren't some academic curiosities, so they widely applied in ecosystem monitoring, precision agriculture, and other main domains. So they produced some extra features that can be used to improve different tasks. How we prepared our data. So as I talked before, we worked with a contrastive learning approach. So we should have a base method as working with triplets. So we have on the left image, from left to right, we can see the anchor on the first row, anchor, positive and negative image of some forest area. And for example, anchor image is some image with masked stressed forest. So these black parts on the image, black regions, are masked stressed forest. Same class images is a positive pair. Is same class image with anchor image. For example, it's masked only health forest as on anchor image, but from other image. And the negative image is masked diseased forest. So also these methods work with diseased forest as anchor image, other diseased forest as same class image, and as negative image is healthy forest from other image. So we provided our anchor model. It consists of 3 parts. First, channel attention blocked. It is marked with a red rectangle. So it uses for adaptive weighting of input channels, and through global averaging, convolutions, and sigmoid activations, we compute the weight coefficients for each channel and highlight some informative spectral ranges. Then it goes to per channel encoders. It marked with blue rectangle. Each channel proceeds with separate small convolution for each channel, and then fusion network marked with green rectangle. It obtained features from all channels and concatenated into single tensor, and then processed with some block of convolutional blocks. Loss function. For training encoder, we use base triplet loss function, but it receive as I said before, masked regions of images. So an anchor image containing pixels of class healthy forest or stress forest, positive image according to anchor healthy or stress forest, and negative image contained only pixels of other class. So after we forward the image of masked image, we receive the embeddings for each part of our pairs, anchor positive and negative, and calculated the loss with such formula, totally basic triplet loss function. Let's talk about experimental results. So to verify our proposed approach, we make like some experiments that conducted in comparing 3 methods for processing Sentinel-2 multispectral imagery. First method uses all 12 original Sentinel channels as input to contrastive encoder. After encoder was trained on these images, encoder converts each multispectral imagery into 3-channel representation, and then we put it into UNet model for semantic segmentation task. Second method applies same UNet segmentation model, but it receives directly 12 channels without intermediate feature extraction stage. And the third method relies on this genetic algorithm that I talked before, that generates multiple vegetation indices, in our case 3, norm P4 and QSimp, from 12 Sentinel-2 channels using labeled pixels. And this genetic algorithm select the most informative index combination, and then resulting feature set used as input to UNet model. We compared dice metric after 3 experiments, after 3 methods. So each method produced us a semantic segmentation mask, and then we compared it by the basic dice metric. Also, we split our data set into 4 parts. 50% of all data used in train, 30% of data used in train, 10% of data used in train, and 2% of data used in train. So you can see the plot of comparing dice metric on a test set depend on train data percent size. So these tables can show us the metrics on each method, and let's talk about the results. So we can see that also I forgot to say that we splitted our train data set each time on 3 k-folds, so we can assume that we don't overfit on some parts of trains that can be like similar with images in test set. So as we can see, with 2% of train size, our contrastive semi-supervised method have overperformed a lot other methods, genetic algorithm a lot, and also row segmentation on 12 channels. Then when train size grows, the difference between metrics reduced, but with 10% of data and 30% of data, it again shows us that contrastive encoder method overperform a lot. But when it when it goes to 50% of train size, the difference between metric on test isn't so significant. So we can say that with a very small percent of data, our method is it shows so much so better results. Yes. This research was in work with these projects. First is Swift, Horizon Europe project Swift, and second one is Horizon Europe project Future 4. So thanks to them. Thank you for your attention. I will glad to ask for, to answer your questions. Thank you.
Hello, thank you for this presentation. Very interesting. Any questions from the audience? Okay, just one little question on this table, actually. I observe here that on diseased forest, in general, the accuracy is worse than on a healthy forest, even with small data set. Have you got any physical understanding of what is this? Have you thought about why this is happening?
Why diseased forest metrics are so much less than healthy forest?
Yes.
Even because as you can see on, for example, this small subset of data, our data consists of, for example, 90 to 10% of healthy forest and diseased forest. So there is a huge overbalanced for healthy forest, and there are not much examples of diseased forest pixels.
So maybe you can try to balance, or if you trained only to recognize healthy, what is left over is diseased, it could be also.
No, I trained and check the metrics on both class, healthy and disease forest, but I have oversampled disease forest and it don't show anything because like we have oversampled same pixels, but the task was like to see the results of experimentally reduce the train size. So I for the reason take the 2% of train size to see the difference of methods.
Or maybe another idea could be to use, for example, 50% or 70% of the test set of the set for training for the disease forest, and only 2% for the healthy forest, so that you have approximately the same size and then train. But yes, this is a room for, I guess, room for future research, probably.
Yes.
Yeah. Okay. Thank you. Any question from the audience? No. Okay. So let's move to the next presentation for paper 98. Petro Peck, Alexander Frolov, Natalia Kristinec, Oleg Kaidik, Sergey Grundyuk, and Oksana Miskevich. Diffusion model framework for text conditioned image synthesis with embedded MQTT communication. So someone here to present paper 98? Someone has shared the screen, so if you can speak as well, we will be glad to hear you. Maybe you have a problem with the sound.
His microphone.
Okay.
Problem is microphone.
Now we can hear you. Thank you. So the floor.
Good day, Sir Nicholas.
Good
Good
morning.
day.
So the floor is yours.
So, thank you. Thank you. Our report is a diffusion model framework for text conditional image synthesis with embedded MQTT communication. Advances is this one. Advances in generative artificial intelligence have enabled the synthesis of high-quality images from natural language descriptions, with diffusion models becoming one of the most accurate and controllable approaches. Unlike earlier generative methods, diffusion models reconstruct images through an iterative denoising procedure, operating in latent space, which significantly improves detail, quality, and semantic alignment. Such models have found wide application in creative media, design, simulation, and visualization tasks. Despite their capabilities, diffusion models typically require substantial computational resources and are therefore executed on desktop plus GPUs or cloud environments. At the same time, modern embedded microcontrollers are frequently used in intelligent systems to monitor processes, collect sensor data, and provide user interaction. The challenge, therefore, lies in combining a powerful generative model with a resource-limited embedded device to create a compact and interactive cyber-physical system. The purpose of this study is to develop and evaluate a system that integrates a Python-based diffusion model with an ESP32 microcontroller operating as a communication and monitoring unit. The ESP exchanges status messages with the server using the MQTT protocol, displays progress information, and enables event-driven control of the generation process. This approach allows the embedded device to participate in workflow that traditionally requires high-performance computing resources. Text-to-image generation has evolved rapidly in recent years, with diffusion models becoming the dominant approach due to stability, high-quality outputs, and controllable generation process. A typical diffusion model gradually transforms random noise into a coherent image by applying a sequence of denoising steps, each guided by a neural network. One of the fundamental mathematical elements of diffusion-based generative models in the photonoising process, in which a clean sample is gradually transformed into noisy representation according to a predefined variance schedule. Compared to generative adversarial networks, GANs, diffusion models provide better mode coverage, reduced training instability, and improved detail preservation. Modern diffusion pipelines, such as stable diffusion, operate not directly in pixel space, but in compressed latent space produced by a variational autoencoder. This significantly reduces computational requirements and enables the use of diffusion-based generation on consumer-grade hardware. The denoising network, commonly a unit architecture with attention layers, predicts the noise components that must be removed at each step, while the text encoder converts the user-provided prompt into condition vector that guides the generation process. Several sampling strategies have been developed to accelerate the denoising process or improve image fidelity, including DD, IM, Euler, Neun, and DPM++ schedulers. These algorithms define how intermediate latent states are updated and directly influence the trade-off between generation speed and the output quality. While the selection and scheduler affects computational cost, even optimized diffusion process still require hardware more powerful than typical microcontrollers. In parallel with advances in generative AI, embedded system and IoT platforms such as ESP32 microcontroller have become widely used for real-time monitoring, user interaction, and external device coordination. MQTT, a lightweight, published subscribe communication protocol, is particularly suited for such system due to its minimal overhead and reliable message delivery. Research efforts have explored in integrating the embedded devices with cloud-based AI services, but the use of microcontrollers to monitor, to coordinate complex generation pipelines unexplored. The approach presented in these reports bridges the two domains by combining a full-scale diffusion model with ESP microcontroller capable of tracking generation progress and interacting with the server in real time, unlike attempts to deploy simplified neural networks directly on embedded platforms. This work preserves the complete generative capabilities of modern diffusion architectures while leveraging the embedded device as intelligent interface. This hybrid design represents a practical example of how generative AI can be incorporated into cyber, physical, and IoT environments without compromising model quality. System architecture. The ESP32 includes a small OLED display which is used to present real-time information such as the current denoising step, scheduler type, connection status, and the completion events. This allows the system to function as a compact cyber-physical installation which a resource-limited embedded device provides feedback on computationally intensive generative process executed remotely. Internally, the server maintains several data structures for coordinating the interaction between the software and hardware components. A progress buffer stores intermediate iteration indexes, timestamps, and predicted noise norms. A message queue is used for publishing MQTT updates, ensuring that the ESP32 receives timely notification even under varying computation loads. The microcontroller in 10 maintains a lightweight state machine that processes incoming messages and updates the display without interrupting Wi-Fi connectivity. Here you can see our system architecture. Connection of the ESP microcontroller with OLED display used for real-time status visualization. To ensure a consistent execution and reproducibility, the server also manages seed, initialization, scheduler configuration, and resource allocation for GPU-based inference, intermediate latent response representations can be stored for debugging or replaying generation runs, while optional logic assists in evaluating model behavior across different parameter settings. This infrastructure allows the system to maintain stable performance even under varying computational workloads. Here you can see MQTT communication sequence diagram. The described architecture separates computational and monitoring responsibilities, enabling diffusion-based image generation to be integrated into scenarios where physical interaction of real feedback is required. This hybrid model demonstrates how modern generative AI systems can be incorporated into embedded environments without reducing their capabilities or modifying the generative code. Algorithm and experimental evolution. The generation process in the developed system begins when the server receives a textual prompt from the user from the ESP32. The prompt is first preceded by the text encoder, which produces a condition vector used to guide the diffusion model. After initialization, the server generates a random latent vector and enters the iterative denoising loop, where the latent representation is refined step by step according to the selected diffusion scheduler. Before the first iteration, the ESP module establishes an MQTT connection and subscribes to status topics published by the server. An example implementation of the function responsible for receiving the text prompt, number of diffusion steps, image resolution and guidance coefficient via MQTT shown in the code provided below. You can see this code. Algorithm and experimental evaluation. Once generation starts, the server repeatedly sends progress messages containing the current iteration number, scheduler name, timestamp, and the intermediate status indicators. These messages are displayed on the HUD connected to the microcontroller, enabling real-time monitoring of the generative process. At each denoising step, the server performs three main actions. Noise prediction. The unit receives the latent vector and the conditional embedding and predicts the noise components associated with the current step. Scheduler update. Based on the chosen sampling algorithm, DDIM, AIR, DPM, or HUN, that next latent state is computed. While the mathematical formulation differs across schedulers, the procedural structure remains identical. The latent vector is updated using the predicted noise and step-dependent parameters. Status publication. A short MQTT message containing the iteration index is sent to the ESP32. Large data transfers are intentionally avoided to minimize communication overhead. After completing all iterations, the refined retained vector is passed through the decoder to obtain the final image. The completion event is sent to ESP32, prompting the device to display a notification on the OLED screen. Optionally, a preview of metadata packet may also be published for external processing. This design separates computation from monitoring. The server performs heavy neural operation while the ESP32 maintains responsiveness and user interaction. The system demonstrates that microcontrollers can participate in high-performance generative workflows without executing the underlying neural model. Moreover, this separation enables flexible scaling of the system. The server-side model can be replaced, upgraded, or reconfigured without modifying the embedded firmware. The ESP32 interacts only with high-level status messages, which ensures long-term compatibility. Even the diffusion pipelines evolve. This modularity also allows the microcontroller to be extended with additional sensors or input mechanism, enabling richer interactive scenarios without increasing computational load on the generative backend. To evaluate the performance of the implemented solution, a series of experiments were conducted using a fixed set of prompts and deterministic seeds. The tests were performed on a local machine equipped with GPU, compatible with PyTorch, and the ESP32 connected via Wi-Fi to the same network. The evaluation focused on the following aspects: generation time under different schedulers, stability and reproducibility of generated images, MQTT communication latency, synchronization reliability between server and microcontroller, correctness of all display updates. 4 schedulers were tested: DDIM, ALR, NUN, and DPM++. For each scheduler, 10 images were generated with identical prompts to observe consistency. The number of inference steps was set to 30 for faster testing, and classifier-free guidance strength was fixed. Here you can see the table with results of our research. DDIM, ALR, NUN, and DPM++. The results show that DDIM provides a faster generation, while DPM++ yields the highest level of detail, consistent with typical behavior reported in diffusion literature. MQTT communication remained stable across all tests. The average delay between a server update and its appearance on the OD was 43 to 55 microseconds under normal Wi-Fi conditions, less more 120 microseconds during high server load. No message loss was detected, demonstrating that small payloads and periodic updates integrate well with the ESP32's processing capabilities. Using a fixed seed ensures that all schedulers produce images with similar semantic content. DPM++ and HAIN showed the more stable fine details, while DDIM sometimes produced slight variation in texture due to its deterministic update rule. This confirms that the embedded device reliably mirrors the server state. The experiments demonstrate that proposed system successfully integrates a modern generative diffusion model with a resource-constrained embedded device using a lightweight communication channel. While the ESP32 does not participate in neural inference, it significantly enhances usability by providing a physical interface for real-time monitoring. The results indicate that the architecture is suitable for prototyping, education, and demonstration of cyber-physical IAM system, and can be extended with sensor or interactive controls in future work. Conclusions. This work presented the design and the implementation of a hybrid software-hardware system for text-to-image generation based on modern diffusion models. The proposed approach integrates a full-scale latent diffusion pipeline running on a server with an ESP32 microcontroller that provides real-time monitoring and interactive controls through MQTT communication and OLED display. This architecture demonstrates that resource-constrained embedded devices can be effectively incorporated into generative AI workflows without performing any computationally intensive neural inference. 2. The developed system successfully precede user prompts, executed diffusion-based generations, transmitted intermediate progress values, and synchronized status updates with the microcontroller. Experimental evaluation using several schedulers confirmed the expected behavior of the diffusion model, while measurements of MQTT latency and OLED responsiveness verified the reliability of the embedded component. The results also showed stable semantic consistency across repeated runs with fixed seeds, and demonstrated that the integration of ESP32 introduced minimal communication overhead. The presented solution can serve as a foundation for interactive generative installations, educational tools, or cyber-physical systems where physical feedback and real-time monitoring are required. Future work may extend the hardware components with additional sensor, integrate bidirectional control for adaptive generation workflows. Thank you very much for your attention, and thank you for watching.
Okay, thank you for this interesting presentation. Any questions from the audience? Just a couple of things for, again, my personal curiosity. So is there the ESP, how loaded is this in this setup? So is there any processing power left for something like security, for example, or you need separate hardware for that?
Sir Nicholas.
Yes.
I am not main author of this work. The main author is my young friends, Frolov Alexander and others, that have another problem. They haven't very good in English, and they cannot, the work is very good, but they cannot give explanation for that. So I thank you very much for ability to be present on conference, but I cannot give more that I demonstrate in my my presentation.
Okay, I understand. So thank you very much.
Thank you very much too. Pleased to meet with you, Sir Nicholas.
Yeah, hopefully we'll meet in person sometime, maybe next.
Of course, you are right.
Situations permit. So just to ask again, is someone for paper AP present? Nural Huliev and Oleksi? No? Okay, so in this case, I think that is the end of this session. So thank you everybody for attending, and enjoy the rest of the conference.